Welcome to the fourth video lecture in the fourth week. We continue with our study of induction. So to recap, we have been looking at the proof techniques, and we have been looking at various different proof techniques for proving a statement like A implies B. We have seen some tricks like how to split a problem into smaller parts, how to remove redundant assumptions, and how sometimes proving something stronger can be easier. We also saw some proof techniques, namely the direct proof, where you prove A implies B directly by working with A, or one can go in the backward direction, namely simplify B to get something simple version of B, namely C, and then one can prove A implies C. That can be an easier thing to prove. We also saw another proof technique, namely case studies, where if you can split the assumptions into parts or cases, then this problem can be split up into smaller problems based on the number of cases. One thing to note here is that the number of cases into which you split up this problem is or should be finite. We also looked at two more proof techniques, namely proof by contradiction and proof by contrapositive. And in both the cases, we look at the problem in a different way, namely proving A implies B is similar to the same as proving not B and A as is false, and this is called proof by contradiction, whereas in the proof of contrapositive, you prove not B implies not A. We have seen various proofs or various problems for which these different kind of proof techniques are applied. So in this week, we have been focusing on another proof technique called induction. So it is kind of similar to the case study proofs, though slightly different, in the fact that here we split up the set of assumptions into not finitely number of cases but infinite number of cases, though countable number of cases, and that induces or that implies that this proof of A implies B gets split up into infinite number of small subproblems, and you have to prove all of them. So subproblems are usually indexed by some parameter of the input, and A implies B is written as P1 and P2 and so on till Pn, and it goes on. We have seen in the last two videos, some examples where how to split the cases or how to split the problem into these smaller subproblems. Now, once we split up the problem into smaller subproblems, we get something of this form that proves prove for all k greater than 1 proves that pk is true. That is what reduces to when we break up the main problem into subproblems. Now, how to go about proving this statement? And that's what the technique of approaching this kind of thing is known as mathematical induction. So usually the idea is that since there are infinitely many subproblems, one cannot expect to solve all the subproblems separately. So instead, we start with proving the first problem. Now, after we prove the first problem, the idea is that if we can prove that for any k greater than or equal to 1, if pk is true, then pk plus 1 is true, then we would basically be proving for all cases. Namely, say we end up proving, of course, this first one says P1 is true, then the second one says that since P1 is true, therefore P2 must be true, since P2 is true, therefore P3 is true, and it goes on like that. And thus we end up proving that for all n, the problem Pn is true which is exactly what we wanted to prove in the first place. Now, why does this proof technique actually work? Now, this works because of the principle of mathematical induction, which kind of guarantees us that it will work. It's a kind of an axiom, and it says that if you can do that, namely first prove the statement for P1 and then for any k, prove that Pk implies Pk plus 1, then you have proved that Pk is true for any k. So a few steps help us to prove for all infinite number of cases. Now we have already seen some applications of this mathematical induction in the last 3 video lectures. In particular, there are different versions of this mathematical induction that one can use. The simplest and the basic version is when we have to prove that for all k greater than or equal to 1, we have to prove Pk is true. In this case, we start with the base case, which says that first prove P1 is true. Then the induction hypothesis states that let Pk be true for some k greater than or equal to 1, and the induction hypothesis or inductive step says that assuming the inductive hypothesis, prove that Pk plus 1 is true. And if you can do that, then we end up proving that for all n greater than or equal to 1, the problem Pn is true. And the induction hypothesis guarantees us that if we follow these 3 steps, base case, induction hypothesis and inductive step, we get the whole proof. Now the second version is when the base case doesn't start from 1. So in other words, it's a slight modification where we say that if we have to prove that for all k greater than or equal to 4, we have to prove Pk is true, then we start with the base case where Pr is true, and then we follow the induction hypothesis, which says that if we assume that Pk is true for some k greater than or equal to 4 R, then by using induction hypothesis, we have to prove that Pk plus 1 is true, and we end up proving that for all n greater than or equal to R, the problem Pn is true. So this is a slight modification from the basic induction hypothesis, and using that one we saw last video how one can solve a problem. So in this video we look at a third version. So in this version, let's start with the same thing. The statement may be that for all k greater than or equal to R, we want to prove that Pk is true. But now I start with a different base case, namely Pr and Pr plus 1 is true. And the induction hypothesis is same, but the inductive step is what makes it very interesting. The inductive step says that assuming the inductive hypothesis, which means that assuming that Pk is true for some k, proves that Pk plus 2 is true. Note that here it is no longer Pk plus 1 but Pk plus 2. And the induction hypothesis basically states that then also we get the whole proof. Now why is this true? As I told you earlier, the whole word is to ensure that for all I, Pi is true. So if you think of this real line and say Pr is somewhere here, then we have the Pr plus 1, R plus 2, R plus 3, R plus 4, R plus 5 and so on. But this says that the base case we have to handle them separately. Maybe we have to prove for Pr plus 1 differently. So we have proved this and this. Now we have to ensure that for all the terms which are on the right side of Pr, meaning all these terms, we are able to prove that Pk is true. The inductive step says that if pk is true from some k, then pk plus 2 is true. Now note that if pr is true, then pr plus 2 is true. Now since pr plus 1 is true, so pr plus 3 is true. Again, since this one is true, pr plus 2, the pr plus 4 is true, and so on. And you can see that we will end up proving slowly that all of them are true. So in short, we have to somehow ensure that all this proof technique, all the dots or all the integer points or all the pk's or k greater than or equal to r is covered by this step. And once we follow that thing, it works fine. So this is the kind of the reason why this particular induction version works. We will see many other induction versions in the coming week, and they will use this very basic idea of filling up or somehow covering all the k's or k greater than or equal to r. Now let us see how we can use this one for solving a problem. So here is the problem. It says that for all n greater than or equal to 1, prove that there exist distinct natural numbers x, y and z such that x square plus y square equals to 4 power n. Now first of all, we have to split this problem up into these cases, right? So what is the kth case? A nice way of putting this kth case will be, of course, put n equals to k, and then it says that pk is the problem. It says that there exist distinct natural numbers x, y, z such that x square plus y square plus z square is 14 power k. And if we can prove this particular statement, means pk, for all k, then we are done. Right? So by now, hopefully you have some idea of how to split the problem into various cases. And we will now apply in version 3 of the induction hypothesis. Okay. So in other words, we have to first prove base case, which says that P1 and P2 are true. In the base case, we have to prove that P1 and P2 are true. The induction hypothesis, of course, says that for some k, let's assume that Pk is true. And in the inductive hypothesis, we will be proving that if Pk is true, then Pk plus 2 is true. Right? It's not Pk plus 1, but Pk plus 2 is true. And induction hypothesis will, the principle of mathematical induction will then help us to state that it is true for all n. So if I put back these things in the base case, what does it mean? It means that first of all, the base case will say that the 14 power 1 and 14 power 2 can be written as sum of 3 squares. Then assuming that the 14 power k is written as sum of 3 squares, meaning 14 power k equals to x square plus y square plus z square for some x square plus y square, so some x, y and z. 14 power k plus 2 can be written as sum of 3 squares. Right? So now our problem is taken care of. We have a base case and we have to prove the inductive step. Now let's go ahead and prove them. Now how to prove the base case? So base case says that 14 can be written as sum of 3 squares and 14 square can be written as sum of 3 squares. Unfortunately, there is no particular proof technique here that one can apply except for finding the x, y, z for each of the cases. So note that 14 can be written as 1 square plus 2 square plus 3 square, whereas 14 square can be written as 4 square plus 6 square plus 12 square. These are some obvious observations that one has to do. So it means that this problem is correct for the base cases or P1 and P2. Now, the inductive hypothesis states that for some k, 14 power k can be written as x square plus y square plus z square for some x, y, z. And we have to prove that 14 power k plus 2 can also be done by that way. Let's see how can it be done. Now 14 power k plus 2 is nothing but 14 square times 14 power k. But this 14 power k of course can be written as x square plus y square plus z square for some x, y, z. That's what is guaranteed by the induction hypothesis. So we have 14 power k plus 2 is 14 square, this 14 square times x square plus y square plus z square, which is 14x square, 14 square x square means 14x whole square plus 14y whole square plus 14z whole square. Now, of course, since x, y, z are integers, so 14x, 14y, 14z are integers, and this ends up proving that 14 power k plus 2 can be written as a sum of 3 squares. Hence proved. Now note that this statement really required the base case to be both of them. If base case was not both of them, then we could not have covered all the integer points, meaning all the cases, and hence we would not have got it. So when you apply a particular mathematical induction technique or proof principle, we just have to ensure that all these points what we want to prove or all the cases are covered. So that means for all k we are able to thus we have proved that for all n, so actually for all n greater than 1 actually, 14 power n can be written as x square plus y square plus z square, but x, y, z are some powers of some integers. This brings us to the end of this particular video lecture. In the next video lecture, and particularly next week, we will be looking at much more complicated induction hypothesis and how we can use them to prove more interesting problems. Thank you.